Soap. Soap is an everyday household item that is central to our lives. Whether it is detergent or hand wash, it keeps us hygienic and clean. To make these soaps, companies use a process called saponification, where a base will neutralize a fatty acid in ethanol and heat, forming a lard-like substance that is the basis of hard soaps. In our lab, we wanted to test the different properties of soap when we use different oils, namely granola, corn, and olive oil, and put them through the process of saponification. Each of these oils consists of a different fatty acid chain that form the soap molecule into a bubble-like structure called a micelle. The different fatty acids have different numbers of hydrogens or the same number of carbons, so the molecular structure of the soap molecule would vary differently.
And I was overwhelmed and frankly scared as hell because I really fell for you. Oh, I swear to you, I'll be there for you. This is not a drive-by. Just a shy guy looking more to fly. Have to bang a whole night. Love more than friends at last. Oh, but that one night is still the highlight. I didn't need you until I came to.
The list of materials that we used in the lab are corn oil, granola oil, olive oil, ethyl alcohol, NaOH, NaCl, distilled water, a funnel, 3 beakers, and 3 50 milliliter samples of water. Using these materials, we saponified the oils and conducted our lab based on the soaps we created.
First, we masked 10 grams of each of the oils in 150 ml beakers. Then we masked 15 ml of sodium hydroxide and 50 ml of ethyl alcohol into graduated cylinders. We then added both the sodium hydroxide and the ethanol to each of the oils, along with a magnetic stir. After, we put the mixtures on a hot plate on high heat and turned on the magnetic stirrers. Once the mixtures were on the hot plates, we began the timers. After the mixtures had been on the hot plates for around 20 to 30 minutes, they began to boil and create a foam. When the foam began to reach the top of the beakers, we began to take the mixtures off of the hot plates. We then measured 20 ml of distilled water and added them to each of the beakers. After, we masked 12 grams of NaCl and added it to 50 ml of distilled water and added them to each of the mixtures. When the soaps had cooled, we put them through a strainer in order to remove the liquids from the solids that had formed. We then masked the 3 soaps to see how much was produced. We also noted that the corn oil was more yellow and more liquid than the canola and olive oil, which formed a more solid and white soap. Next, we began to test the properties of the soaps, starting with the pH. We first masked 1 gram of each of the soaps and added 20 ml of water to it. We found that each of the soaps had a pH of 12. After testing the pH, we then tested the melting points of the soaps. Using a temperature gauge and a heat plate, we connected it to the computer to create a graph that would show the temperature changes occurring within the soaps. We found that corn oil had a melting point of 77.7 degrees Celsius, olive oil had a melting point of 74.8 degrees, and canola oil had a melting point of 52.9 degrees. Our last test was to determine the effectiveness of the soap. We created a scale from 1 to 5 to determine how effective each soap was. We then mixed water with mud and created 3 stains on a t-shirt to test each of the soaps. We first masked 1 gram of each of the soaps and added 10 ml of water to each of the beakers and stirred it with a stirring rod. We then let the soap sit on the stains for 30 seconds. After, we scrubbed each of the stains for a minute, trying to maintain the same pressure for each. As a result, we found on a scale of 1 to 5 that olive oil had an effectiveness of 4, canola oil also had an effectiveness of 4, and corn oil had an effectiveness of 4.5.
Originally, we thought our data may have not been accurate because as the number of hydrogens increased, the melting point of the soaps decreased. However, all the fatty acids have the same amount of carbons, and the number of hydrogen atoms correspond to how many double bonds are within the molecules, as you can see in these diagrams. These were cis bonds that cause kinks in the chain of fatty acids, so the greater the number of double bonds, the weaker the IMFs. As the number of hydrogens decreased, the number of double bonds increased, so the weaker the IMFs and lower the melting point. This may also explain why effectiveness decreases as the number of hydrogens decrease, as the weaker attraction forces meant that less dirt will be suspended by the soap micelle. In conclusion, based on the data we collected, we found that oils with more hydrogen had weaker bonds. Although the pH of the soaps remained the same, an increase in hydrogens in the oils caused a decrease in effectiveness and temperature of the melting points of soaps.